I'm Ben Darnell. I'm the co-founder and CTO of Cockroach Labs. I'm here to talk to you today about CockroachDB, which is a new distributed transactionally consistent database that we're building. This talk is going to have a little less Go-specific content than most of what's going on today, but we are building the database entirely in Go, and I'll talk a little bit about how that's working out for us. Also, before we begin, it's important to note that the database is 100% open source under the Apache license, so you can use it for whatever you want. So today I'll start out by giving you a little background on the database and the company and how we got to where we are, what problem we're solving, trying to provide a mix of consistency and scalability that you can't really find in any other options on the market today. We'll talk about how it works, how it's built up from the ground up, show you a little demo, and then talk about our use of Go and where what we're building going forward. So, like I said, Cockroach started as an open source project in early 2014, when it was just a side project for a couple of developers. And then at the beginning of this year, in February, we founded a company to work on it full time. We're up to 10 people now. We're based in New York City, and we recently closed our Series A funding from Benchmark, Google Ventures, Sequoia, and FirstMark Capital. And so really what we're trying to do with Cockroach is address this dichotomy in the database market, which is that you have essentially two main categories of databases. On the one hand, you have relational databases, which have been around since the 70s and are the de facto standard for this kind of thing. And they have a lot of great features like declarative SQL interface, good support for indexing and query planning, and they give you transactions so that you can make consistent changes across the database. But they have a lot of trouble scaling up, or they're expensive to scale up, and they have a lot of trouble scaling out to large distributed clusters. And so in the 2000s, sort of following the lead of Google's Bigtable and other early systems that kind of broke away from the SQL tradition, there's been a lot of effort to create what are known as NoSQL databases, which give up a lot of the features that you see in a relational database in order to make scaling easier. And so these databases are easy to run in large clusters, and they can be highly available depending on which specific database you're talking about and how it's configured. But there are a lot of limitations that go along with that. Chief among them that you don't have transactions, and so it's easy for your data to become inconsistent among your different shards and replicas. And then there's also a lot of features that you don't have, like joins. You have to do that manually. In many systems, you have to maintain your own indexes. Sometimes there are things that you just can't really express easily. And so what we believe with Cockroach is that it's possible to So you have a dilemma here where you have to choose between these two sort of polar opposites of a consistent database or a scalable database. And with Cockroach, we believe it's possible to have both. And so we're building a SQL database with the scalability of a NoSQL solution that still has all the features and transactional consistency that you would expect from a relational database. So you can scale out a Cockroach cluster among many machines over a wide distribution area, and the data remains absolutely consistent, and it remains consistent and available even in the face of failures of machines or even entire data centers or regions. And this is the property that gave the project its name. The database is going to be about as difficult to kill as a cockroach, and hopefully will be the last database standing after a nuclear holocaust. So now I'm going to walk you through the design of Cockroach, starting at the lowest level and show you how we build up to getting these three key properties. First of all, at the lowest level, when you consider just Cockroach running on a single machine, it's built as a sorted monolithic map. So even though the the data is divided up into tables and rows and columns and all of that. Everything is internally structured as if it's a single sorted key value map. This is a very good general primitive to build on. It's what both Bigtable and Spanner have been built on at Google, and so we're sort of following in those footsteps. And so we have a map that just contains all of the data in the database, encoded in a unified way. And then as you put more data into this map, eventually it reaches a maximum size, and when that happens, we want to split the data up so that it can be accessed as separate units. And so we call these splits ranges. So the conceptual monolithic sorted map in CockroachDB is actually made up of a series of ranges, each one covering a contiguous range of the key space. And so you have one range that contains keys from the beginning of the alphabet, and then the next range contains keys from the next portion of the alphabet, and so on. And this range will continue. The data will continue to grow and split into new ranges as data comes in. It doesn't. You can see here it's not always perfectly balanced, but it aims to keep the ranges in a relatively consistent size. Our current target size is about 64 megabytes per range, so that gives you an idea of there could be a very large number of ranges on one node, but the ranges themselves are still small, which is good because it makes it much more efficient to move ranges between machines. And so this is how we scale the system out to multiple nodes. We take the ranges and we move a range at a time onto a different node. And so we can see here that one node still has the first two ranges, but the system will see that there's a second node in the system that doesn't have any data at all, and so it will start moving some of the ranges over to this second node, and so on throughout the cluster. And so each range is moved to a machine that has space for it, has capacity available in multiple dimensions on disk, and as well as memory and throughput and that sort of thing. And so here we have this design gives you a very scalable database that can run across many different nodes, but it's not yet fault tolerant. If any one of these nodes goes down, then you've lost that chunk of data. And so to make the database more survivable, you have to replicate the data. And so here we can see that the range has there are two ranges that have been split, and then each range is replicated on three nodes. This is a configuration option. In general, you'll run Cockroach in a way in which each range is replicated either 3 or 5 times. It's important that that this be an odd number because internally things are based on elections and quorums, and you want to have an odd number of candidates so that you don't run into tied votes. And as the database grows, the ranges are all replicated independently, and so we can see that ranges may be co-located with each other on some replicas and not on others. And that's fine. The system just bounces at the level of the individual range replicas and moves them where space is available. When you have data that is stored across multiple machines like this, it's of course very important that the data be consistent across these replicas. And so the replication system actually uses Raft as its consensus protocol. Each range is an independent instance of the Raft protocol and the Raft state machine. And so we have many sets of nodes all independently running Raft and conducting elections amongst themselves. And so in any group of replicas, one of the three nodes will be elected as the leader. The leader is the one that coordinates all the decisions for the group. Whenever you want to write something to the database, that write goes to the leader to be proposed to the cluster, and the leader considers it committed as soon as it has been acknowledged by a majority, in this case 2 out of 3 of the replicas. For the the actual implementation of the Raft protocol, we share this implementation with etcd, built by the CoreOS team, and so this has been a very good collaboration for us because it's helped both sides get a more complete and robust implementation more quickly. Although our use is a little different from the typical use case for Raft, because in most cases you're running one instance of Raft with a handful of replicas. And in Cockroach, we run many instances of Raft, some of which will have overlapping replicas and some will not. And so we have a layer on top of Raft, which we call multi-Raft, which basically groups up messages that are bound for the same node and helps amortize that cost so that we're not sending one heartbeat message every second for every possible pair of nodes, or actually we are sending it for every possible pair of nodes. We're not sending it for every possible pair of range replicas. And so that reduces the messaging overhead of keeping track of the independent replicas. And so Raft gives us consistency of individual keys and or really multiple keys if they all fall within the same range. If the keys are not in the same range, then we need to supplement Raft with a higher level distributed transaction protocol. And so we implement distributed transactions using what's known as optimistic concurrency control, which means that rather than grabbing a lock and holding it while we execute a transaction, we write what's called an intent, which is a special record into the database to say that this transaction is in progress. And during the transaction process, we detect if there are any conflicting intents, and if so, one of the transactions gets selected to be aborted and restarted from the beginning. And so this performs very well under low levels of contention, which is the vast majority of cases in practice. As long as your data doesn't involve a lot of conflicting writes to the same keys at once, then this optimistic concurrency control can be much more efficient than using locks. Also under the hood, we use multi-version concurrency control, or MVCC. So we make older records available for read-only use, so that you can do a read-only transaction at a consistent point in time without having to block concurrent operations, and writes can proceed in front of that transaction. In SQL, you have a choice of isolation levels. You may be familiar with these terms if you've used relational databases. You have a choice of things like read committed, repeatable read, serializable. In Cockroach, we also offer a choice of isolation levels. We only have two options. Our first isolation level is serializable, which is at the top of the traditional SQL isolation level pyramid, and it provides the most consistent. It's the most consistent mode of operation. There are no opportunities for transactional anomalies to show up when based on the interleaving of different transactions. But sometimes it can perform poorly, especially, as I said, under high levels of contention. And so we let you opt into a lower level of consistency called snapshot isolation. And this will, this is kind of analogous to the difference between repeatable read and serializable in a traditional SQL database. It's not exactly the same thing, but it's similar in the sense that you're seeing a consistent snapshot of the view, of the data, which may not be exactly the most up-to-date information, but that's frequently enough for most cases. And so sometimes if you're experiencing a lot of contention, you may want to opt into this snapshot isolation mode. Although we do have the default set as the highest level of isolation, as opposed to what's normally done with SQL databases, where you start with the most performant option and expect users to understand when they need to ratchet that up to a higher level. We believe that it's important to provide the safety by default and to let users opt into the higher performance when they need it, instead of the other way around. Finally, given all of these building blocks, the interface that you use to interface with the database is SQL. We're using a more or less standard dialect of SQL. Start using the Postgres dialect as our starting point. We're mostly compatible with Postgres, and as it turns out, SQLite. SQLite has a very extensive test suite, which we found to be very easy to adapt to our use, and we already can pass a very large fraction of that test suite. And so really our goal with providing SQL is that you can use this under the hood with any standard object relational mapping, whether that's GORP or Squalor or any of these, any database abstraction that you may care to use, or in other languages, Active Record, SQL Alchemy, whatever things you want to use. So we may not, we're not sure yet how much of the SQL standard we want to support, but we definitely want to aim for enough standard compatibility to let you use any database abstraction as kind of a drop-in replacement. And so that's been kind of a whirlwind tour of the design of Cockroach. I want to make sure I haven't lost anybody too badly. Are there any questions at this point before I continue? Yes.
Just a quick question. I just wondered, when you talked about locking, are we talking at the stable row level, or are you talking at column level, or underneath?
As for locking, well, as I said, we do multi-version concurrency control, so there is not actually any locking involved. But the intents that we write are at the key value level in the map, which is done at the column or the cell level, kind of the intersection of a column and a row. We're still, I think we're still sort of working out how we want to expand that and make sure that all of the right cells are locked or implicated in the transaction at the same time. But yeah, it's very fine-grained locking in SQL terms.
So I just wondered what the mapping was between. I kind of thought that it might be something like that, and I was wondering how you were honouring the SQL transaction semantics.
Yeah. So I'm not sure what exactly SQL requires of transactions in terms of row level locking, but our current implementation is done essentially at the column level. So two transactions on the same row can proceed in parallel as long as they touch a disjoint set of columns. Yes.
Just to get a sense of context or scale, what's your target for the maximum number of concurrent ranges in a single database right now?
We don't have a firm number for this, but we are explicitly drawing inspiration from a lot of Google's technologies, Bigtable and Spanner and so forth, and so we're aiming to support petabyte scale clusters. Supporting we don't have an upper bound in mind. We want to be able to grow to as big as necessary.
Before they were unceremoniously bought by Apple, I was doing a lot of interesting looking at FoundationDB, which seems, at least in marketing terms, a lot like this. Is that a fair comparison? Are you targeting the same space? Is it the similar technology?
Yes, that's a fair comparison. FoundationDB was one of our closest competitors technology-wise. All right, so we have this. So we have this very feature-rich and consistent database, but of course that's not very useful if it ends up being tremendously difficult to run. And so we're also putting a lot of effort into making deployment as simple as possible. Everything in the system is symmetric. We just give you one binary with no external dependencies. You don't have to have Zookeeper or anything like that running. You just take the binary and some TLS certificates, put it on a node, start it up. You don't have to designate nodes as master and slave or primary and secondary or anything like that. It just self-organizes. The nodes talk amongst themselves. They have a gossip network to discover where exactly the data lives, and that they will elect leaders as needed, and the system will automatically detect imbalances in load and move the data around. And so our aim is to make this as extremely easy to use. We want it to be as easy as anything else on the market to get up and running, just from just running one process on your laptop to running a small cluster in the cloud to running a full data center scale deployment. And so I'm going to give you a quick demo of how this works. We have this is not the best demo here because it involves just a lot of log messages running by in a terminal, but it's hard to make these databases visible in a demo. So I'm just going to initialize a cluster here, which is a little script I made to run through some initial steps, which this basically just creates the TLS certificates that are used for authentication. And now when I start the first node, it's running in a very verbose mode, so you can see things, a lot of stuff scrolling by. It's really not easy to follow, but you can see the color-coded entries at the beginning of the line. You see there's a lot of red and yellow there indicating that something's wrong. In this case, it means that this node is trying to talk to its peers and it can't find any. And that means that the data is under-replicated, critically so at this point. There's that you're one failure away from data loss. And so it's trying to find its peers and not succeeding. If I go ahead and start up a second node, then it's going to connect to the first node and pick up a replica of the data. And if I look in here, we do have a web UI behind a broken certificate. And we can see here that we have two nodes running, and the data is available because we do have two nodes running, but it's not fully replicated. The data is still not up to its target level. If I start up a third node, now once that has finished syncing up, now you see that the red and yellow messages have stopped. If I come back to the web interface, in a few seconds we should see this fully replicated number go to 100%. And there it is. This is unfortunately not very observable, but this means that the data is running on all three nodes. And now I can load some data into it, and you see we have a basic shell prompt, and still some rough edges here, but we can see that there is a basic shell interface, and it can accept commands. And let's see, but rather than make you watch me type out commands by hand, I'm just going to run a pre-written example which simulates a simple bank that stores account data in Cockroach and moves money from one account to another, and make sure that the data is still transactionally consistent, which means that you never have a case where money is added to account A without being subtracted from account B, or vice versa. So you want to make sure that the total amount of money in the system is constant. And you can see here that if I kill off one of the nodes, then the log goes crazy. Everything is spamming lots of error messages, but the client keeps on going. The client is just fine as long as there are two of the three nodes running. If I then kill off a second node, then the client suddenly stops working because you can't make any progress when you don't have a quorum of nodes available. And so everything is going to grind to a halt until I bring one of the down nodes back, and this will take a second to sync back up. But as soon as it does, now the client is back up and running. So this is just a quick demonstration of the fault tolerance of CockroachDB. So now I'm going to shift gears a little and talk about how we, since this is a Go conference, I'm going to talk a little bit about how we use Go. Overall, this has been a great experience for us. A lot of us on the team were new to Go. This is the first project in the language for a lot of us, and we found the learning curve to be very quick. Much easier to learn than any other language that we've worked with, especially compared to C++, which was the last systems language that most of us spent a lot of our careers in. There's a couple of techniques that we've hit upon that we found really helpful and might be interesting to a wider audience that I'm going to talk about here. One is something that is some things that we've done to optimize our memory allocation and garbage collection. And then second, I'll explain a little bit about how we manage our non-Go dependencies. So one thing that people ask us a lot, especially people coming from a C++ background, is people wonder what we're doing trying to write a database in a garbage collected language, because people have had bad experiences with the JVM garbage collection or other garbage collected languages. This can be a large expense. It turns out that in Go we really haven't had a problem with this. We've ported we haven't done a lot of memory profiling of CockroachDB yet because we're still building the core functionality. But in other systems, we've ported a large system from Java to Go and greatly decreased the memory footprint and garbage collection overhead. And a lot of that is because Go gives you the tools to manage your allocations in a way that Java really doesn't. You can combine things that would be separate allocations in a typical garbage collected language and put them into a single struct. And then there's also a few advanced tricks that you can use that I'm going to explain here. This is a bit of code from the part of Cockroach that reads data from disk and decodes it out of RocksDB. So here we have we declare a type, the GetBuffer, which is a buffer that includes a couple of different structs inside it. The MVCC metadata and MVCC value, these are both protobuf objects. We use Google protocol buffers to store everything on disk. We also use a third-party library called GoGoProto instead of Google's own protobuf library, which we highly recommend. It follows a lot of these same principles that I'm discussing here to avoid unnecessary allocations. And so we have these embedded in the GetBuffer struct. So we have one allocation instead of three. And then on the third line, we declare an array. You don't see array types in Go as much as you see slices, but when you have an array like this of a fixed size, that can be done directly in the struct without an extra allocation. And I'm going to come back to this point on the following slide to show how that can be used. On the right-hand side of the screen, you see the use of a sync.pool. Sync.pool is another feature that Go has. This is a relatively recent addition. I think it was added in 1.4, and it's a little subtle. It wasn't. It took me a long time to figure out what this was actually for and why I would want to use it. But what it does is it's a simple free list that lets you reuse objects that have already been allocated with that, and so that you don't have to allocate another object that's going to have to be collected by the garbage collector later. And so the way you use it is by just declaring a global sync.pool object with a factory function, which in this case just allocates a GetBuffer struct and returns it. And then when we use it, instead of just making a GetBuffer, we can get one from the pool, and the pool.get returns an empty interface, which we have to type assert to the correct pointer type, and then when we're done with it, we put it back in the pool. And so this this means that in the common case, we don't have to even do the one allocation to get the buffer struct. And then the array that we use, arrays and slices are distinct types in Go. Nearly everything deals in slices rather than arrays, and so you can get a slice from an array just by using the square bracket syntax. And the nice thing about this is that you can then you can create a zero-length slice, which we say here by doing buff.keys 0:0, and that creates a zero-length slice backed by the array. And the fact that this array already has this backing, that the slice already has this backing storage behind it, means that any appends that you do to it will actually go into that array instead of creating a new allocation. And this is all done transparently as long as there's room. And so in this case, when we're decoding the key that we read from RocksDB, we can append it to a slice created out of this buffer, and then as long as that key is less than a kilobyte, we don't have to allocate anything. It just reuses the array that we already allocated. If the key is over a kilobyte, which is possible but less frequent, then it transparently allocates a new backing array, and we don't have to actually be aware of that. We can just use this transparently. And so by combining these techniques of putting multiple objects in one struct and using a sync.pool and a pre-allocated array for our slices, we've managed to get rid of all of the Go level allocations from the critical path of reading through RocksDB entries. Up next, so we have a number of non-Go dependencies in CockroachDB. The biggest one is RocksDB, which I've mentioned briefly. Just to explain what that is, it's a database library. It's open source. Actually includes code from both Google and Facebook in it. The original version of this code was called LevelDB and released by Google as open source. It was originally built for storage of bookmarks and other local data in Chrome. Facebook took it and forked it and renamed their version to RocksDB and made some optimizations that make it very good as a server-side database. And so it has better support for large data. And this is actually our lowest level data storage system. This is what actually manages the bits on disk. And so we have RocksDB. We have a few other things like the snappy compression library and Google's protocol buffers. These are all things that these are all C++ libraries that we want to be able to use from Go, which is easy to do with CGO, but there's if you don't have these libraries installed in your system in userlib or wherever, then it becomes fairly complicated to manage these things. And so originally what we did is the same thing that most people do in this situation. We had a little wrapper make file which would run make in RocksDB and Snappy and everything else, and install them into some prefix, and then set the right CGO flags to make everything build. The problem with this is that this wrapper make file kind of defeats the whole point of Go Get and the unified Go toolchain. If you have to run a make file instead of just Go build, then that becomes a barrier to downloading and just getting started with a code base. It also, as we found, it breaks compatibility with a lot of the source analysis tools. In particular, Go Oracle was not happy with the way we used to do this. And finally, versioning becomes a real headache. We had a lot of situations where whenever any of these C++ libraries was updated, we would need to manually run a make clean and a rebuild just to get things working again. And so the way we solved this problem was by actually getting rid of the makefile and doing all of our builds in Cgo without any other build system for the C++ code. The way this works is we take the source distribution from the third-party library, and we just untar it and take all of the source files out of it and put those in a directory in the Go package tree. So under Go path source, github.com, etc. We take all the C++ source files, we put them in a directory with one Go file, which doesn't contain any actual Go, but it just contains the metadata for Cgo to build it. This is an example of one of these files. This is for our Snappy package, which is the simplest of the ones we have to deal with. It's the only one that's small enough to be legible on a slide. So as you can see, this is the entire file. It's just a package declaration, an import, and then the Cgo flags. The Cgo flags here are things like compiler flags. In this case, it tells the compiler to use C++11. Sets config path and sets the include path and some other defines. And this is basically, if you run the /configure script in this directory, these flags are kind of what that's doing, what that's spitting out into the makefile. And so we would run the configure script to set that up with everything it needs, and then instead of actually using the makefile that it generates, we would recreate those same options in Cgo. And so the nice thing about doing it this way is that once you build your dependencies like this, the entire Go toolchain, including both the standard tools like Go Git and third-party things like Go Oracle and other tools, they all just work. And so this is how we're able to actually be compatible with Go Git, even with a fairly complicated set of dependencies. This does have some drawbacks. It's not as portable as the real configure script. You have to sort of transpose everything that configure does into something that's simple enough for Cgo to understand, and Cgo only gives you a limited set of configuration options. But for the set of the set of libraries that we're using, this turns out to be fairly simple, and so we were able to convert all of our C++ dependencies to use this system, and that has really simplified our build process, and then it also solved the versioning problem, or at least it reduced the versioning problem to one that we already had to solve anyway to the way that we manage our Go dependencies. But these things can be vendored just like a Go dependency or whatever other dependency management tool you use. So I've given you an overview of what we've done so far, and so the project is not finished. We're still sort of in the early alpha stages of development. So what's left for us to do? Our big projects right now are in a number of different areas. The biggest thing that we're working on right now, and the main thing that's blocking us from being really usable for more serious purposes and large-scale testing, is the rebalancing system. We need to build out the systems that will detect when the cluster is imbalanced or when a node is dead, and will take that data and make sure that it gets replicated appropriately to a different node in the cluster. We're also working on the admin UI, the web page that I showed you briefly earlier. We're working on fleshing that out so that it can be a good overview of what's going on in the cluster, and hopefully you won't have to spend any time staring at log files like we've been doing for months. We also want to have good deployment tools. We have a simple tool now that will set up a cluster on either EC2 or Google Cloud, Google Compute Engine, and this is still a work in progress. We've got to figure out how we want to handle the TLS certificates and that sort of thing, but it's this will be our main main way to get a cluster set up very easily from scratch. And then finally, the SQL layer is one of these projects that will never truly end. There'll always be more work to be done in terms of adding more feature sets and more features, more optimizations, and better compatibility with the rest of the SQL ecosystem. So if any of this interests you, we'd love to hear from you. We have as I said, everything is open source. You can see the code on our GitHub page. We have a lot of things in our issue tracker that are tagged according to how to what might be easy things for third-party or outside contributors to get started with. And so, if you'd like to take a look and help us out there, that would be very welcome. Or if you're not interested in contributing and just want to use it, that's great as well. It's a little rough right now for someone who's using it rather than developing it, but we're working on that, and it's improving rapidly. So in conclusion, we want you to stop saying "or" about your database choices. We want you to be able to get all of the properties you need: scalability, consistency, and survivability, as well as all the features that you need to make your applications work, so that you can concentrate on your application logic and not in how to get the database to do what you want or work around the database's limitations. So if you'd like to get in touch with us, here are all of our links. We're on GitHub, website, Twitter, and with that, thank you, and I'd be happy to take any questions.
Hi, hello. If you run CockroachDB over multiple data centers, which let's say 2 replicas in London, 1 in New York, what kind of impact does that have on write performance?
So if you run in multiple data centers, there will be an impact on latency, of course. Every write needs to reach a quorum of nodes, and so you inherently have to cross that inner data center link. We do put a lot of work into minimizing the number of round trips there, and so a distributed transaction can be completed in as few as 2 round trips between your data centers. It's going to, in practice, it's going to depend on exactly how your transaction is structured, but we do intend for this to be a major use case, and so we want to make sure that we minimize the number of round trips as much as we can.
Just to first of all to say it's really impressive. With the reads from the database, if you've got a large database that's being used for perhaps some sort of archival and analysis, you might be reading from quite a large range, which typically seems to trip up things that are distributed performance-wise. So do you have to be aware of where the data is, some sort of locality and where you run your queries, or does it scale automatically?
So this is for the it's going to depend on what exactly you're trying to do. If you're doing something simple that you can express in a SQL statement, say you want to so if you can say in your SQL statement, like select average of this field grouped by X, then that's fine. That's going to do the work on the nodes where the data is, and then only send the aggregates back to the client. If you can't express what you're doing in a SQL expression, then for now, yes, it will have to bring all that data back to the client and do the work there, and that will be that will be very expensive. And that's something that we would like to provide more options for in the future. Whether that's something like stored procedures or maybe MapReduce or coprocessor style of thing, where you can send application code somewhere close to where the data is. But right now, the only interface we anticipate in the near future for that is going to be SQL, as far as getting data to where getting code to where the data is.
So I know that you're still working on rebalancing, and perhaps the answer to my question lies there.
Mm-hmm.
But when you have to split a range into two new ranges because it gets too big, are you currently trying to do something clever, like getting them in different nodes, everything like that, or just basically leaving them as is, because this may make the nodes very unbalanced?
Yeah, so it's actually, so splitting is actually independent from rebalancing. And so when a range is split, the new range has exactly the same set of replicas as the original one. It just splits in place. And then separately, the rebalancing system will come along and consider these ranges for rebalancing. But it won't. We don't automatically say that as soon as a range splits, we try to move the new subranges apart from each other.
Hey, thanks for the presentation. It's really quite impressive. The thing with Google style and Facebook style sort of databases is that there is often a minimal viable deployment, as in 5 nodes or something like that. Is there any limitations for Cockroach that you right now foresee that at least you have to have a certain node set or data set to be viable?
Yeah, so the minimum in practice is going to be 3 nodes, so that you can have the ability to survive one node failing. It will also work in a single node deployment, with the caveat that single node is, it is what it is, and if that disk goes away, then you've lost your data. But it could be viable for you to have a single node deployment backed by a RAID array or some sort of underlying reliable storage.
Hi. Do you plan on only supporting a SQL API going forwards, or are you going to continue to support the KeyValue API that currently exists?
So this is I understand that this is kind of a contentious point in the community. We've decided to go along with the SQL interface as the only interface at this point. We believe that we can do a KeyValue API as a layer on top of the SQL interface without causing significant overhead. If that turns out to not be true, then we'd be open to reopening some sort of dedicated KeyValue API. But right now we're treating our KeyValue layer as kind of an implementation detail behind the SQL layer, rather than as something that we want to support for applications to talk to directly.
Hi, so this is kind of touching on a previous question. So, for instance, MySQL and Hive have struggled, and they've worked really hard to optimize how logic is pushed down onto different nodes. I was wondering if you had any stories or any experiences that you might share on how you've approached the problem and any challenges you might have faced.
Unfortunately, I don't really have any stories to share about that. This is more of a longer term vision that we're thinking about. So in the near term, it's as I said, it's essentially SQL. So if you can express what you want in a SQL expression, it'll get pushed down to the nodes, and if not, then you have to pull the data back to yourself. I think that that there are a number of interesting avenues to go down. Google has done a lot of things in this area in terms of the way that, for example, their MapReduce scheduler is aware of GFS chunk locations, or Bigtable and Spanner have a feature called coprocessors to run application code near where the data lives. I think things like this could be very interesting for us in the future, but they're really too far away for us to have any concrete plans for at this point.
Hi. You said that you're in early alpha at the moment. What's your kind of release roadmap? When are you hoping to go beta and 1.0?
So we're hoping to have a beta ready to go by the end of the year. As I said, the biggest single blocker for that is the rebalancing and repair system, and we also want to do some additional work to make sure that we're not going to have to change the on-disk format or network protocols or anything like that after we call it beta. We want to make sure that people can rely on things not breaking out from under you at that point. So we're aiming for beta at the end of the year, and then over the course of the next 6 months or so, for it to mature to the point where, depending on your personal risk tolerance and appetite for living on the bleeding edge, you may be able to start using it for real data.
Hi, thank you very much. This is really exciting. I was wondering how do you guys handle replications, specifically that you have two replicas of the same range. How do you figure out which changes are in one and not in the other?
So this is where Raft comes in. Raft is a distributed consensus algorithm in the same category as Paxos. And so whenever any change comes in, each replica maintains a log of all the changes that have been made, and a change is considered to be committed once it has been acknowledged by 2 out of 3 of the replicas. And so whenever there's whenever the leader of a range goes down, the other 2 ranges will conduct an election. One of them will be elected the leader, and then they will compare their log positions to see what they both have, and then that's the committed point moving forward.
Cool. Thank you very much, Ben.
Thank you.